Hello to all physics enthusiasts and fans of physical experiments. This is Alexei Kolchin with you, and today we're going to talk about a phenomenon known as the stability of floating bodies. And when I was in school studying Archimedes' principle, it was only about the condition for an object to float. But how exactly would the object float? That was never discussed. And they would draw pictures like this: a floating square section block with a density equal to half. And it was depicted like this. But now I'll show you that such a block won't float that way. And for this experiment, we've prepared a block of extruded polystyrene foam with weights placed along its axis so that its average density is half that of water. Now I'm placing this block with its top face parallel to the water's surface. Letting go, and it tips over onto its edge. Well, let's try flipping it onto another face and repeat the experiment. I let go of the block, and once again it tips over onto its edge. But if I take a block made of pure extruded polystyrene foam, whose density is 40 times less than that of water, it floats quite stably on this face. Moreover, it can even float on this other face, and it hardly tips over at all. To understand what's happening, let's take a look at the hull of a ship floating on water. Two equal and oppositely directed forces act on it: the force of gravity, applied to the ship's center of mass, and the buoyant force, Archimedes' force, applied to the center of mass of the water displaced by the ship. This point is called the center of buoyancy. Now, let's imagine that the ship has tilted to one side. It might seem that the resulting moment of these two forces would cause the ship to tilt even further. But we need to take into account that the underwater part of the ship is no longer a rectangle and has become a trapezoid, because the right side of the ship has sunk deeper into the water, while the left side has partially risen out of the water. Therefore, the center of buoyancy also shifts to the right toward the submerged part. If the center of buoyancy ends up to the right of the ship's center of mass, then the combined moment of the two forces will restore equilibrium and return the ship to its original position. And such a ship is said to be stable. But if the moment of the forces were to cause capsizing, the ship would tip over and sink, as has happened more than once in the history of shipbuilding. And one of the most famous cases is the disaster that happened to the flagship of the Swedish fleet, the warship King Gustav Vasa in 1628. Due to improper centering, it capsized and sank. But before we move on to theoretical calculations, let's experiment a bit in the GeoGebra program. And we'll start with a square section block with a density equal to half the density of water. Let's return to our original experiment, but here everything is quite simple. The center of gravity of this block is always located at the water's surface and doesn't move anywhere. But the center of buoyancy shifts to the side. And you can see that a moment of force appears, causing the block to tip over more and more. But look now, when the block has sunk with its edge down, this moment becomes zero and the block is in a stable position, just as we saw in the experiment. Now let's do a second experiment with a wide block, which should clearly be stable. We start to rotate it and see that the force arrows diverge in completely different directions, creating a significant restoring moment. And of course, such a block is stable. And now here's the experiment that seemed the most interesting to us. We rotate this block and see that an overturning moment appears. But look closely, the blue arrow, representing the buoyant moment, overtakes the red one. As a result, the net moment becomes a restoring one, causing the block to stop its motion and settle into this stable position where it floats at a distinct angle.
And now, in this video, I appear as the theoretician. And I want to find out how the center of buoyancy of the block shifts when it is slightly tilted. Here, a rectangular block is shown, tilted at a small angle alpha, and the blue area represents its submerged part in the position when there was no tilt. It will be convenient for me to denote the width of the submerged part as 2a and the depth of immersion of the block in the neutral state as 2b. So at the beginning, the center of buoyancy was located at the distance b vertically from the middle of the deck, and we will look for the displacement of the center of buoyancy when tilted, relative to this initial point. It will shift by some amount along the x-coordinate and rise by some amount along the y-coordinate. So by how much did it shift along the x-coordinate? Well, if the center of gravity of the rectangle shifted by a distance of alpha b along the x-axis. But we also had this little triangle that rose above the water and this little triangle that went under the water. We also need to take into account the mass displacement associated with these triangles. And here I add the following term, alpha a squared. That's the area of this triangle and the area of that triangle combined, divided by 4ab, that is, this area, the ratio of the masses. And I multiply by this lever arm to the center of mass of the triangles, but obviously it's 2/3 of the deck's width, that is 2a divided by 3. In exactly the same way, we get the vertical displacement of the center of buoyancy. Well, here we have, again, the vertical displacement written out for this blue rectangle when it tilts. Well, here it will be alpha squared times b divided by 2, and here in exactly the same way, the lowering of these points by an angle of alpha over 2 relative to, and the raising respectively by an angle of alpha over 2 relative to the horizontal is taken into account. And the main thing to derive from this, so to speak, is that the x displacement is proportional to the angle alpha, while the y displacement is proportional to alpha squared. Therefore, for small alpha, the curve along which the center of buoyancy moves is a parabola. Y is proportional to x squared. Well, a parabola has a certain center of curvature. We find this center of curvature, we find the corresponding radius. And this radius equals b, that is, this distance from the middle of the deck to the center of buoyancy in the neutral position, multiplied by a certain coefficient, 1 minus a squared divided by 6b squared. Now let's consider two floating bars, one with a wide underwater part and the other with a narrow one. Let's assume that in both cases the center of mass is underwater. We will conventionally show the direction of the bar's tilt by moving the center of mass along an arc of radius s. Now let's find out where the center of buoyancy has shifted. If the underwater part is wide, so that the squared is greater than 6b squared, the radius of curvature r actually turns out to be negative. This means that the center of the corresponding arc, which in ship theory is called the metacenter, is located below the center of buoyancy. Therefore, the centers of mass of the block and the centers of buoyancy move in opposite directions, and the resulting moment of forces returns the block to its original position. And when the underwater part of the block is narrow, the radius of curvature r is positive, the metacenter is above the center of buoyancy, and the block will be stable if the center of mass shifts more than the center of buoyancy. Therefore, the condition for stability is that the radius r must be less than the radius s. And now we will express the condition for stable floating of the block in the non-tilted state. That is, the condition of stability, as sailors say, in terms that are convenient for us. Here I have drawn the block once again, and now I will use its dimensions. So, the width is 2a. The height, it's convenient to write it as 2h as well. And the depth of immersion, as we denoted it, is 2b. And it's clear that 2b to 2h, or simply b to h, is in the same ratio as the density of the block to the density of the liquid. This is a direct consequence of Archimedes' principle. And now we substitute everything into the previously obtained stability condition, and as a result, we get the following formula. The block floats stably without tilting if the ratio of a to h, that is, width to height, is greater than this square root of 6. Here we have the density of the body over the density of the liquid, and here is the second factor, 1 minus the density of the body over the density of the liquid. And now we can show on a diagram the regions of stable and unstable floating for a rectangular block resting on one of its faces. When the density of the block is half the density of water, a block with a square cross-section cannot float stably on any of its faces. For stable floating, the width of a block with such density must exceed its height by at least 1.23 times. And for a square block to float stably on its face, its density must be either less than 21 hundredths of the density of water or greater than 79 hundredths. And this can be tested experimentally. The fruits of theorists' imagination are wonderful, but unfortunately, perfect parallel pipes exist only in the world of Plato's intelligible ideas. But when you start making an experimental object, it turns out that there are major problems with centering. So we were not able to make a stably floating brick with a side ratio of 1.23 and a density of 1/2. But this brick here has a density of 1/2 and it floats perfectly, very stably, whether on one face
or on the other face, but its side ratio is only 1.45. And we were not able to improve this result significantly.
However, I must say that we shouldn't discount theory. After all, without theory, we wouldn't know anything at all. Yes, we did have some issues with this brick, because in order to achieve a density of 1/2, it had to be centered. But we can take a brick made of pure penoplex, give it the shape of a rectangular parallelepiped, and experiment with such an object. Its density is 1/40th that of water. And when we substitute this 1/40th into the formula, we'll even take into account this bracket, 1 minus 1/40th. We'll calculate it with that level of precision. We find that the critical ratio of the parallelepiped's width to its height is 0.38. And now Alexei will definitely take this and test it in practice.
So let's start the experiment with this block, where the width to height ratio is 0.44. And it floats perfectly, very stably. You can even rock it a bit. Now let's increase its height so that the width to height ratio becomes 0.42. And it still floats. Alright, let's add another plate. Now the ratio is 0.40. And remarkably, it still floats. So now let's add another plate on top, bringing the height to width ratio to 0.38. And it quickly tips over to the side.
This result is exactly as our theory had predicted.
So we've taken a look at the theory of the stability of floating rectangular homogeneous blocks, and now it's time to move on to some practical recommendations. Well, with blocks, it's all very simple. Since we can't change the center of gravity of a homogeneous block in any way, the only recommendation is to make it wider. That's it. But for real ships, this recommendation is far from always feasible. For example, yachts need to be narrow enough to reduce water resistance. So in this case, they take a different approach. They lower the yacht's center of gravity as much as possible, and to do this, they add a false keel loaded with cast iron or lead ballast. And now it's time to move on to our traditional final question, which will be related to underwater swimming. We have a challenge for you. Try to formulate the essential stability criterion for submarine navigation. And then please write your answer down in the comments section for our video right here on YouTube.